Okay, so with that, it's my great pleasure to introduce Milind Tambe. Milind is my colleague at Harvard Computer Science and also leads the AI for Social Good effort at Google Research India. Milind is a renowned AI researcher. He's made seminal contributions to multi-agent systems, especially to areas like multi-agent teamwork and cooperation. In the last 15 years especially, has become one of the most prominent voices on AI for social good. He's had stunning success getting government agencies around the world to adopt his work on challenges like fighting crime and terrorism, wildlife protection, and public health. Now, one reason Mike and I were enthusiastic to bring Milind to EC is that his work in AI for social good is grounded in models that are at the heart of this community, like game theory, equilibrium computation, and influence maximization in social networks. In this sense, it's the epitome of the type of work promoted by the wonderful Global Challenges in Economics and Computation program, which is featured at the conference. So I'm very excited that Milind is with us today, and with that, I'll surrender the virtual floor to him.
Wonderful. Thank you. Thank you, everybody, for coming to this seminar. Thank you for this very kind introduction. Very excited to be here. So with the current progress in AI and multi-agent systems, it is now important to direct these advances towards societal impact. In my research group, we have focused on 3 topics: public health, conservation, and public safety and security. In all of these areas, viewing these societal problems as multi-agent systems, there's a key research challenge that we focused on: how to optimize our limited intervention resources when interacting with other agents in these domains. With respect to public health, the challenge is that we have limited number of social workers, limited public health resources. Concrete example is work we've done in homeless shelters in Los Angeles. Harnessing the social networks of homeless youth, we are able to show that our influence maximization algorithms are far more effective in spreading HIV information compared to traditional approaches. The key area I'll focus on, of course, here is social networks. With respect to conservation, we have large conservation areas to protect, limited number of ranger resources. The challenge is then how to optimize the use of these limited ranger resources. Harnessing past poaching data, we are able to predict where poachers set traps or snares. In our work in Uganda and Cambodia, for the past many years, we've been able to remove thousands of these traps or snares. The challenge I'll focus on today here is green security games, combining machine learning and game theory. With respect to public safety and security, we've contributed a new model called Stackelberg security games and contributed new algorithms that have been in use by security agencies such as the Federal Air Marshal Service or the US Coast Guard. I'll not discuss this work today, focusing instead on public health and conservation. These topics of public health and conservation are also at the heart of our effort for AI for social good at Google Research Bangalore. Working with many NGOs that are featured here, we're working on topics such as maternal and childcare, or warning farmers about human-animal conflict so that they can better take care of their crops. I'll focus on one of the projects here today, just given time limitations. So in all of the projects, you'll see 3 key themes that cut across. First, the use of social networks and game theory or other multi-agent reasoning approaches. Second, this data to deployment pipeline. We start with the process of immersion in the domain, often working with the NGOs to understand their constraints, to understand the kind of data that they have available for the problem at hand. Following that, a predictive model, this is where machine learning may come in, may help us make predictions on the data in the case of a domain involving risk prediction, separating out, predicting high-risk cases against low-risk cases. Next, a prescriptive algorithm. This is where the multi-agent systems reasoning comes in. This recommends to us which cases to actually intervene on. Given that we don't have enough resources, we have to select which of our high-risk cases, for example, to intervene on, and that's where the multi-agent reasoning systems will come in. Finally, what's crucial for us is field testing and deployment. This is where we can begin to understand the limitations of our models and algorithms and continue to improve them. And the real world also gives us hints as to what structure in the domain we can exploit in order to improve our models and algorithms. Of course, the reason we do this field testing and deployment is because we are really interested in social impact. This is AI for social impact, and social impact is a key objective as first-class citizen of this research universe. Secondly, you'll see throughout my presentation, we're supposed to be swimming in large amounts of data, but in reality, in many of these domains, there is a lack of data. And so this lack of data is a norm, and we find that it must be part of our project strategy. A final common theme is interdisciplinary collaborations with different NGOs around the world. The work we do is in service of the work that's being done by the NGOs to assist them in their work. To that end, we've really patrolled with the wildlife conservation agencies in forests to understand their constraints, spend time in homeless shelters to try to understand what constraints they operate under. This understanding is crucial in developing models and algorithms that are suitable to the task at hand. So as I go through the rest of the talk, I hope there are 3 key takeaways that the audience can get out of this presentation. First, EC research, the research done by this community on multi-agent systems models, whether it's social networks or game theory, are very useful, impactful for public health and conservation projects, as I hope you will see. Deploying things in the field, though, brings up new, exciting research challenges, which I hope would be of interest to the EC community, and I'll outline some of these challenges. I hope that we can collaborate on some of these challenges as we go into the future, and work on these would be extremely valuable for challenges in public health and conservation. And finally, for those who are interested in working on these topics, there's a wealth of multi-agent research challenges when we partner with NGOs. So with this introduction, let's get into the 2 topics of public health and conservation. I'll start with information dissemination in social networks, talking about health program adherence and then agent-based modeling. I'll cover papers that we've written from 2017 to now in conferences such as AMAS, AAAI, HCA, and others. I'll highlight the role of the key PhD students and postdocs by putting up their picture in the top right-hand corner. There are many other collaborators, including those in the audience. I will have their names on a slide right at the end to acknowledge all the contributions from my co-authors. So let's start with the social networks. So motivating domain I'll use is preventing HIV amongst homeless youth. There are 6,000 homeless youth, for example, who sleep on the streets in Los Angeles every night. The rates of HIV amongst these homeless youth are 10 times the rates of the normal house population. So homeless shelters try to spread information about HIV prevention by recruiting peer leaders, informing them about HIV, and these peer leaders are supposed to talk to their friends, and their friends talk to their friends, and information spreads in the social network. This is real face-to-face interaction, not Facebook, etc. Whereas I've used this domain as a motivating example throughout the talk, you will see that there are many other applications, whether it's HIV prevention among sex workers, as we are doing with this NGO called Swasti in Bangalore, or tuberculosis awareness, or other such challenges. So this is the problem of influence maximization that the EC community, of course, is very well aware of. You have a social network graph G, you're choosing K peer leaders to maximize the expected number of influence nodes. And information we assume is spreading, in this case, in an independent cascade model. When we inform youth A will inform youth B, and information will spread in a cascade. Applying this model, this influence maximization approach in the real world with these homeless youth, raised 3 new challenges. First, there's uncertainty in propagation probability over edges in the graph. Second, we are interested in multi-step dynamic policies because we cannot bring in all peer leaders all at once. And when we bring them in stages, what we find is some peer leaders may be no-shows, they can't appear. And so we have to take into account who showed up in the previous stages in order to compensate by adding new nodes or dealing with the contingencies that may arise. We also have no observation of the state of the network. So this is different from adaptive influence maximization. And finally, we have an unknown social network, and we can have a limited query budget to uncover the network. So let's start with challenge number one. We have uncertainty over this propagation probability. When we talk to youth C, we're supposed to generally, in the normal models, know that there's this probability, let's say 0.4, that an adjacent youth D will be informed about HIV prevention. But in reality, of course, there's uncertainty. We can model this by sampling from some distribution. And then to further model uncertainty, we can say the mean of the distribution is also something we're uncertain about and lies within some interval. So this is now a challenge of robust influence maximization. We try to come at it by building up an algorithm that's going to play a zero-sum game against nature. So our algorithm is going to choose a mixed strategy over policies for peer leaders, selecting peer leaders, and nature is trying to choose parameter settings to cause our algorithm to perform as worse as possible, where the payoff is the outcome of a policy for a particular parameter setting to the optimal policy that could have been achieved for that parameter setting. So we are playing this max-min game. And of course, so to illustrate this, consider this 2x2 game. We have an influencer, which is trying to choose policies, but picking particular peer leaders. And nature is trying to choose parameter settings to cause our algorithm to perform as worse as possible. Of course, this is a massive scale game because the influencer has a large number of selections. If you have a node, if you have a graph of 800 nodes and you're trying to select 20 or 30 peer leaders, there's a very large number of strategies for the influencer, a very large number of strategies for nature as well, choosing from a continuous interval. So to handle this, we use a double oracle approach. We start with initializing the game with a small number of strategies for both the influencer and nature. And then we solve this game, find equilibrium, and then the influencer's oracle will provide a best response to this mixed strategy of nature and add one particular strategy for the influencer. Then nature will provide its best response to the mixed strategy of the influencer, adding its best strategy, and the game will grow. And again, we solve for equilibrium, and we iterate in this fashion until convergence. And often this convergence is found without iterating too much with a very few number of strategies. Now, when we know that we have an exact best response from the influencer and nature, we would converge to the actual equilibrium. However, here we are forced to use approximate oracles on both sides. And the key is then to show that we can converge with approximation guarantees as we show in this paper. So next is the challenge of multi-step policies. We want to invite, let's say, 20 peer leaders to show up at a homeless shelter, but we can't accommodate all 20. So we may only be able to bring in, let's say, 4 peer leaders. So we invite 4, and then next week when we want to bring in, or next day when we want to bring in the next 4, what we find is that in the previous day, the 4 we invited didn't all show up. Maybe only 3 showed up. It's also possible someone sent a substitute. So the next day's 4, the green dots, need to take into account who showed up in the first time step. So this is a problem of, given a history of who was invited as peer leaders, who was absent, figure out a policy to decide who to invite in the next time step, where the state of the network is unobservable. This is essentially, this problem is planning under uncertainty. We can solve this as a POMDP, where it is choosing nodes at every time step, getting observations on node presence. Solving these POMDPs is difficult. A paper at AMAS tries to provide heuristics and techniques to try to speed this up. One particular point to highlight is noticing that this homeless youth community is made up of clusters of sub-communities, youth who hang out on the Venice beach together, youth who play basketball together. And so we can exploit this community structure. For example, in the 2 networks, example networks here of Hollywood and Venice of homeless youth, what we find is that if we create these communities automatically partition, that only 12 to 15% or so of the edges cross these communities. So exploiting these local communities allows us to achieve efficient performance with POMDPs. The final problem is data collection is costly. If we have our social workers sitting in a homeless shelter, trying to figure out who's talking to whom to build a social network, that's time consuming and costly. Could we sample small fraction, let's say 15 to 20% of the network, and use that for influence maximization? So the challenge here is that given a set of nodes N, we have to build a sampling algorithm that can query until a query budget, and then output a set of K seed nodes that if we use them to spread influence, that they'll compare favorably to an optimal approach, an optimal result we can achieve if we use the best influence spread by an algorithm that knows the full network. So the sampling algorithm we built samples nodes randomly, estimates the size of the communities these nodes belong to, and then choose seeds from the largest case communities. And we can show that for community structured graphs, the sampling algorithms obtains a constant factor approximation to the optimal influence spread using polylog and queries. Okay, so now we've got the 3 components in place, and we built a system called Sampling Healer, where we got network sampling, this robust multi-step policy, and we can start executing peer leader selection. Now, in building this system, we can prove results about individual components. An open challenge is really, how do you provide guarantees on the performance when you build this whole system and put all these different components together? And I hope we can get some people excited about solving this problem. It was now time to try to understand how these sampling healer algorithm performs in practice via pilot test first. So we created 4 separate experimental partitions. So first one is sampling healer. I emphasize the word sampling because in this arm, we have a sampled network of homeless youth. So you recruit 60 youth here. There are 2 versions of healer, both with knowledge of the full network. This, again, we recruit 60 youth each. And degree centrality, this is the more traditional approach. Bring in the most popular youth. And in each case, in each of these 4 partitions, we selected 12 peer leaders. Here's a picture from our social work colleagues educating these peer leaders about HIV prevention. And the question then becomes, how many of the non-peer leaders, those we did not bring in, actually got informed about HIV? So first, let's look at comparing healer and degree centrality. Both have knowledge of the full network. And what we find is that among the non-peer leaders, those we did not bring in, 75% of those got informed about HIV when we were using influence maximization algorithms, and only 25% when we were using the traditional approach, bringing in the most popular youth, use degree centrality. So clearly, influence maximization algorithms are useful in spreading information more effectively. Now the question is, what if we sample this network? So what will happen to sampled healer? And here we find, again, that 80% of the non-peer leaders got informed about HIV. The numbers are slightly higher even than knowing the full network, but that's just because of the small variation in network conditions. And again, the main point is that this is much better than degree centrality. So sampling healer is the algorithm of choice that we now want to take to a full large-scale study. Now, the Journal of Social Work article that you'll read about this, if you choose to, you'll find that there's only 1 paragraph of description about the AI algorithms, because the social work colleagues are very keen on understanding what is the actual impact on behavior. And the article goes into a lot of details on that. So that's what we want to study next. Is there an actual impact, actual change in behavior of the homeless youth as we do a large-scale study? So we did a study with 800 youth. The results have just come in. This is led by my friend and colleague, Professor Eric Rice of social work. And as far as we are aware, a first large-scale application of influence maximization for public health. This is done in collaboration with 3 homeless shelters, My Friend's Place, Los Angeles LGBT Center, and Safe Place for Youth. So first thing we look at is HIV risk behavior is a reduction in condomless anal sex. So we ran the study, and at the end of 1 month, looked at this change in behavior. And here we have sampled healer causing about 35% reduction in this HIV risk behavior. Degree centrality, which was the second arm, had no impact, and control group, where there's no intervention, no impact. At the end of 3 months, we find that with degree centrality, it has begun to catch up. It's getting closer to sampling healer, but it took 3 months to get there and still not there. Now, reaching more youth more quickly is really important because first, this is HIV risk behavior, which we want to reduce as quickly as possible. And second, this is a transient community. People often leave. And so it's important to reach them more quickly. The paper that's under submission, it's also an archive, provides more details on other kinds of metrics. But here's another one, reduction in condomless vaginal sex. And again, you see that sampling healer at the end of 3 months has reduced this significantly more than degree centrality. All of this has led to excitement amongst our partners. And here's a sampling of their reactions.
Beautiful way to kind of like marry this tech world with this social service world, like, and how we can kind of go deeper and impact young people and elevate them.
If this group became a really big thing, it could really help out a lot of youth.
So we have continued trying to investigate other algorithms for sampling and influence maximization. In our A-RMAB 2020 paper, we look at using a reinforcement learning-based approach. So here we start with a small graph, a small social network, and then we query nodes. And as long as we are under query budget, you continue to query further nodes. And when you exceed it, you run influence maximization, get rewarded, learn from that. This approach improves performance over the handcrafted algorithm that I mentioned earlier from IIIT, for example. But this is an open area for further work. There are many other interesting challenges in use of social networks and their applications. We've investigated others. For example, suicide prevention is a major topic, whether it's homeless youth or kids on college campuses. One approach that's taken is gatekeeper training. So you train a set of gatekeepers who keep an eye out on their peers. If we select a gatekeeper and they notice somebody in their peer group who says something like, you know, sometimes I want to sleep and not get up, then they can refer them to counseling or have counselors approach them. So the question is, we can't train a lot of gatekeepers. So which gatekeepers would you train in the network? Now, not all gatekeepers will come to a training session. Not all gatekeepers will fulfill necessarily all their tasks. So the question becomes one of robust graph covering. We'll select a few gatekeepers, but not all will show up. So we want to be able to robustly cover the graph. If you use standard robust graph covering algorithm with gatekeepers to maximize worst case coverage, one challenge we face is disparity of coverage across racial groups, as we've seen here in this concrete example from a homeless youth network in Los Angeles. So we are exploring challenges to handle this using different fairness approaches. One standard approach is a max-min fairness approach that we report, incorporating that within this challenge for in Europe's 2019. Another is diversity constraint. So this is the idea borrowed from cooperative game theory, where idea is that each group should be able to get as much coverage as they would if they were to separate out from the community and get number of gatekeepers proportional to the size of that community. Let me now, I guess the final point here is that this is a topic that's of interest to us across many of our projects in public health. And for this particular project, we are waiting for IRB approval in order to make further progress. Let me now switch to health program adherence. I'm going to talk about passive and then active adherence. And I'm going to bring up two separate domains. The first one is maternal and child care in India. The situation is difficult. A woman dies in childbirth every 15 minutes in India. 4 out of 10 children who are born are too thin or short. And so we are very honored to be working with an NGO called A-RMAB, which works with 18 million women and 160,000 health workers and so forth. One of their programs is called M-Mitra, Mobile Friend. It provides a weekly call to new and expectant moms. It sends a friendly 3-minute message every week. So a call given in the voice of the local health worker about things like, okay, you are in the 3rd month of pregnancy. You should go see a doctor to, do this checkup. Things of that nature. And A-RMAB has shown that there's significant benefits if expecting a new mom completes this course, which is about 140 phone calls from pregnancy all the way to the child being 1 year old, that there's significant benefits in terms of health of the child and mother. They have got 2.2 million women who have enrolled in their program M-Mitra so far. One challenge though is that there's a significant fraction of these women who are low listeners or drop out. And then the question becomes, can we predict which beneficiaries, which women are likely to drop out of the program? And that would allow A-RMAB to focus their intervention, allow health workers to focus to try to retain these specific women who we have pointed out are at high risk of drop-off. So here's how this is supposed to work. You have mom number one. Arman calls them first week, she doesn't pick up her phone. Second week, third week, and so forth, she listens to the message. Mom number two takes the phone call on the first 2 weeks, doesn't take the call in the third week, takes the call in the fourth week, doesn't take the call in the fifth week, and so on. And you can imagine hundreds of thousands of women with these kinds of phone call patterns. It turns out in this simple case, mom number 2 and 4 become low listeners, drop out of the program. If we could have informed Arman ahead of time that just by looking at the listenership pattern in the first few weeks, that mom number 2 and 4 at a high risk of drop-off, then that would allow their health workers to focus on trying to retain these moms in the program or give them other counseling. We've built a neural network system for making these predictions. It worked extremely well with past data. And now the question was, can we do a pilot test? So we did a pilot test with 18,000 beneficiaries who were enrolled and looked at their call pattern, listening pattern in November and December of 2019, and tested this for January and April through data on January through April of 2020, and found that our predictions were very accurate with respect to recall, precision, all these values being over 0.8. And so today, this prediction software for Arman is actually deployed in practice with the NGO, and it's helping them with their 300,000 beneficiaries in a Mitra in predicting these high-risk beneficiaries. And they have already started seeing returns on retaining these beneficiaries in their program by intervening on them. A second problem I wanted to point out, a second domain is tuberculosis prevention. Tuberculosis is still the largest killer on the planet despite COVID-19. In India alone, tuberculosis kills about 500,000 people every year. 3 million are infected. And one big challenge is non-adherence to TB treatment. People are supposed to take their pills for 6 months, but they may drop off after a few weeks. So there's these digital adherence tracking techniques. So basically in the pill box, in the sleeve, as you open each pill, there's a random phone number, and you're supposed to call it every time you take the pill. By looking at who's been calling, health workers can track who's adhering and who's not adhering. So the key challenge for us is to intervene before patients miss doses. So if a person doesn't call for a few days and then you go and tell them that, okay, you're missing your doses, that's a little too late. Can we predict from the pattern of phone calls ahead of time who's at high risk of missing their doses? And so this is work we've done with an NGO called Everwell, taking data from Mumbai, India, 15,000 patients, 1.5 million phone calls. We're able to show that our prediction works significantly better, 35% improvement in true positives, reduction in false positives compared to their standard rule-based approach. So this is again on the way of being deployed. So I have so far talked to you about predictive modeling, prediction for high-risk cases. Now comes the job of the multi-agent systems reasoning, where I hope will get your interest even more. Now I'm going to, for expository purposes, simplify the situation and assume that we are not getting any predictive information. And now we have to actually check with the actual patients as to who's adhering and who's not. So here, health worker is going to call and patients are not going to call. This is the situation we faced in Mumbai in January, for example. They said, we've run out of those sleeves that have the random phone number, so health workers are calling. So this is how this is supposed to work. We have a health worker which may have 200 patients in their care, and they are going to call the patients. They can't call all of them. They'll call a few patients every day to track and improve adherence. So this health worker may call, say, the first 3 patients, check, are you taking your TB medicine? And find that 2 of them are, 1 is not. We have no idea what's happening with the remaining ones. And they call patients in some kind of round-robin fashion, trying to understand who's adhering, who's not. And this is a 6-month course. And so you can keep calling patients to try to get information on adherence and encouraging patients to take their pills. So this can go on. Question is, could we do better than something like a round-robin approach? And so we are proposing a approach on adherence restless bandits. And I'll explain what I mean by that. So some of you may be very familiar with restless multi-armed bandits. So this is a specialization of that model where each arm here is a health worker calling a patient. So each arm has basically pulling an arm is calling a patient. So each arm here, a patient has a binary latent state of adhering or not adhering. When an arm is not played, when a patient is not called, the patient may change his state. And so we have some belief that we may modify when we don't call them as to that the patient is reducing, there's a lower probability that the patient is adhering to taking their medicine. When the arm is played, when you call the patient, you get observation as to what happened yesterday, and you can encourage the patient to take their medicine, so there's a higher chance of adhering in the next round. So given this model, the question is, can we solve this efficiently to come up with a policy to advise health workers? When all of these transition probabilities are known, and this is an assumption we've made here, one of the basic theorems we're able to show is that this adherence restless bandits can be indexable if the threshold policies are optimal. And indexability is important for performance guarantees on this adherence of restless bandits. So what's a threshold policy? You call a patient, our belief that the patient is adhering goes up. You don't call, the belief starts going down. When the belief goes below a threshold, we call again. And then again, when we don't call them, the belief starts to go down. So we can show that this forward threshold policies are optimal if the intervention effects on non-adherent patients is large. Empirically, in the data we have, we find that almost all patients are threshold optimal. And so we can have a fast algorithm without sacrificing performance too much. And in fact, we are able to show that our algorithm generating policies for calling these patients runs significantly faster than the best baseline we could find in this area, and without losing much in solution quality. Key assumption here we have made is that we know the transition probabilities, but of course, one of the interesting challenges is how do you provide guarantees when we don't have that and information ahead of time. So I'll end this section by talking about COVID-19 agent-based modeling. This is recent work that we've engaged in. An agent-based model that we've constructed has families, comorbidities, age, testing, contact tracing, an SCIR model. Early results from this got picked up in the media about our predictions of Georgia and Florida and so on. But more recent work has looked at COVID testing policies. For example, what should a place like Harvard do? Should we be testing all of the students every day? And what kind of tests should we use? A gold standard test like PCR detects viral concentrations. It's very sensitive, but costs a lot. Something like an antigen strip is much less sensitive. So if it turns out that we can we can run the less sensitive test over the entire population and the more sensitive test on the entire population at the same frequency, then indeed the more sensitive test would reduce total number of infections. However, the more sensitive test often has 1 day delay in reporting. Just that 24-hour delay causes the more sensitive test to be less effective. So here, if a person is seen to be positive, we quarantine them. That 1 day delay causes the number of infections to rise. Furthermore, if the more expensive test can only be run less frequently, like every 5 days, again, the number of infections rise, leading us to the conclusion that test sensitivity is secondary to turnaround time and frequency for COVID-19 surveillance. I was delighted to find in the July 15 summary of Nature's papers on COVID-19, they've talked about this paper today. So in terms of summarizing key challenges that I hope would be of interest to researchers who are in the audience. First, with respect to influence maximization, are there any performance guarantees that we can provide when we have this combination of an unknown social network and want to have a robust and dynamic policy? What's the right influence model? We've used independent cascade, but the actual data on the ground on how information spreads has led us towards other models. For example, we proposed this activation jump model for A-RMAB 2018, in A-RMAB 2018, that sometimes seems to do better. So understanding the right model and fairness in influence maximization is, of course, a key challenge. With respect to Bandits for health adherence monitoring, I talked about efficient algorithms. We assumed certainty of patient observations. We also assume known patient behavior, unknown and evolving patient behavior, uncertainty of patient observations. are clearly open challenges, and enabling community health workers to interject in intervention planning, because they're not just necessarily going to take the recommendations of our model and just run with it. So these are some very interesting open challenges to us. I hope they're of interest to the audience. Let me now switch gears and talk about conservation. This is Murchison Falls National Park in Uganda. I'm going to use wildlife conservation as the main motivating domain here. Wonderful wildlife, but there's threats to the wildlife, snares or traps, thousands of them that are used to kill wildlife. So we have a small number of rangers. So one approach to try to give them effective patrol routes is to model the problem as a Stackelberg security game. So we are going to take the Queen Elizabeth National Park, divide it up into 1 kilometer by 1 kilometer grid squares. Each grid square is a target where there's water, for example, more animals, more important target, and we can then try and solve the game and generate patrols. But there is a difference compared to traditional approaches. So for those who may not be familiar with the model, basically in a Stackelberg security game, you may have these areas that a ranger is supposed to patrol, and a poacher can make observations about what patrolling has happened in the past month or even past year, and then choose where to place the snare. So it's a Stackelberg game, and generally we would want the ranger to use some randomized patrolling strategy to improve their expected utility. One key difference with previous work, which had focused a lot on fully strategic adversaries, here with poaching, we are faced with boundedly rational poachers. We're trying to learn adversary response model at each target eye then based on the data that's available. So we're going to take the data, make predictions on adversary behavior, and then solve a game and then deploy the generated patrol strategies in the field. So we have, for example, 12 years of poaching data from Uganda on ranger patrol frequency in each grid square. We have information for each grid square on distance to rivers, roads, and villages, area, habitat, slope, and so forth. And we're trying to learn an adversary response model to our ranger patrols. There's one challenge. When the rangers report that they found a snare, yes, they have found a snare. When the rangers report they didn't find a snare, it could just be they just walked a little bit more, they could have found a snare. So our level of trust in their negative instances, negatively labeled data, depends on how much walking has been done in that particular grid square. So based on this, so we have this challenge of learning from positive and unlabeled data, where our level of trust in these negative instances depends on the level of walking in that grid square. So to handle this, we created this imperfect observation ensemble model. So we create multiple filter data set. For example, in this filter data set, we remove all negative instances where patroller has walked less than 1 kilometer. We don't trust that data. Here, when a patroller has walked less than 2 kilometers, we remove all those negative instances. And so for each of these filtered data sets, we construct a classifier. And then at test time, when we get an instance where a patroller has walked less than 2 kilometers, first two classifiers will apply. More than 2 kilometers, other classifiers will come into the picture, and so forth. In the lab, of course, we can show that our model performs better than other machine learning approaches that we could use. But the real test is on the ground. This is what Wildlife Conservation Society and Uganda Wildlife Authority wanted us to check. Can we predict in new spots where they hadn't patrolled as much, where they hadn't found any poaching incidents, could we predict new poaching hotspots? And so this was a challenge that we took up. We predicted these 2 9-square-kilometer areas where there were infrequent patrols. This happened to be 1 month before an A-RMAB deadline, meaning that if our predictions worked out, we would be able to write a paper for A-RMAB. If not, no paper. And so we made these recommendations of where they should patrol. You can see these green dots. This is where these don't overlap with the red dots where previously poaching incidents had been found. And now rangers went out on patrol, and every day for a month, they're supposed to tell us what had happened. Initially, there was no response. And then as they patrolled, they reported back a poached elephant with its tusks cut off. It is a sad event. Certainly, we were too late to save this elephant. But at least the machine learning, our adversary response modeling was pointing us in the right direction. Then came great news. We found a whole elephant snare roll. This is the actual picture of that elephant snare roll, and removed it. So poachers were active in the area. They were killing elephants, but before they could kill the next set of elephants, we were able to remove the snare roll, hopefully saving lives of elephants. Then whole antelope snares were found. And so this first pilot was seen to be a success in predicting new areas where poaching is going on and removing snares. Then came the chance to actually do a large-scale test. So this was a test in 2 national parks in Uganda, run for 6 months. We selected 24 areas in each national park. We predicted some of these to be high risk, more snares found, some to be low risk, less snares found. The key being that just because, and if you said for any infrequently patrolled area you're going to find snares, that's not useful. We need to be able to discriminate. Some of these less infrequently patrolled areas are high risk and some are low risk. And that was the goal here. And indeed, we are able to show that our model works quite well in making predictions where we said they were high risk. More snares were found and less when we predicted low risk. Same thing in Murchison Falls, where we predicted high risk, more snares were found. Here we've said high, medium, and low. In fact, the work has been continuing in other parks, like in Cambodia, Srepok Wildlife Sanctuary. Here's snares that have been found based on our predictions. Again, our predictions of high, medium, and low, you can see that they match. Where we predict high risk, more snares are found. Numbers of snare captures have jumped more than 5-fold. The park manager tells us that whereas previously rangers would go out and find 10 or 20 snares sometimes per patrol, now they come back with 100 or 200 snares. And in fact, very exciting, our collaborator, Rohit Singh, head of zero poaching effort of WWF, talking about how he's super excited with the results and wants to deploy this across the world. And I'll come back to this point a little bit later on. So before we go on, one challenge is that, okay, so we've made good predictions about adversary behavior. Are the adversaries actually observing our patrols and reacting to them? There is understanding informally in the conservation community that the adversaries, the poachers are reacting to our patrols, but not a quantitative model. So we built this model to try to understand how much or if there is a reaction that's going on from the poachers to our patrolling effort. And what we find is indeed there is a positive coefficient for the current effort. So the more you patrol, the more snares you found this year. But the poachers are repelled by, there is a deterrent effect. The poachers don't visit the areas as frequently as shown by the negative coefficient. So if you patrol an area frequently, next month or next year, the poacher will not visit those areas. So this justifies our Stackelberg model. And so the next step then was to apply the Stackelberg security game model to generate patrol routes. Now, generating patrol routes is a very complicated task. There are many constraints on patrols. To understand these constraints ourselves, we've gone on patrols ourselves. So this is one picture of our patrol in Malaysia. Beginning of the day, we are so happy, oh, we're going to go on a patrol. And then middle of the day, hacking through the forest, you can see thoroughly exhausted at the end of the day, realizing we need to make improvements to our models. So there's a lot of very interesting things to talk about, but I wanted to highlight one paper from EC'20, which may be of interest. So here the challenge is how to build a better adversary model when there is insufficient data. Bad model obviously would lead to errors in planning patrols on targets. And here we propose this game-focused learning to maximize decision quality. The key point being that maximizing learning accuracy doesn't translate into maximizing decision quality. So consider a situation where we have only 4 targets for illustrative example here, and we use standard loss function in order to maximize accuracy in adversary value estimates on each of these 4 targets. Then we generate patrols, but what we find is that 2 of the targets have a large effect on defender expected utility. What this means is really when we were trying to learn, we only needed to learn accurately if our estimates for the 2 targets that really matter and not really spread our error and not really bother as much about errors on these other targets. So this is the idea of game-focused learning, is to maximize defender expected utility directly during learning. And so to modify the loss function to take into account defender expected utility. And this leads to better patrols in simulations. This has shown better results. So in terms of gradient descent, instead of passing gradients back from just learning an accurate adversary model, here the idea is to go beyond, solve the game, and then pass a gradient back from the defender expected utility. There are many interesting challenges with respect to counterfactual reasoning and so forth that are outlined in the paper. In simulations, we can show that game-focused learning, when there are patrolling constraints, does do better. Testing this in the field is our next step. There are many further areas of interesting work on, for example, incorporating network security games to prevent illegal smuggling and so forth in the same paradigm. So I'm assuming, Ariel and Yana, that I have about 5 minutes or so. Is that right? Maybe 5 to 7 minutes?
Yes, perfect.
Great. So in the last section, I wanted to talk about incorporating real-time information. So far, I've talked about incorporating past poaching data. So now this real-time information is going to come back to us in terms of drones. So this is work we've been doing with Air Shepherd in South Africa. They fly these drones at night and take infrared video. They send the video to a van where a human being is looking at those videos, looking for heat signatures of poachers, and then try to alert rangers to come and stop poachers. This is very difficult for a human being, so we built a system called Spot to automatically detect poachers and animals. This has been delivered to Air Shepherd. The idea is to automatically detect these because making the task easier for human beings. So this is how it's supposed to work. The drone will fly overhead, automatically detect poachers. We alert rangers to bring them in. Unfortunately, the probability that a ranger may arrive is small, for example, 0.3. So there's a high chance that a poacher may not be stopped. In these situations, the Air Shepherd uses deceptive signaling. So when there is no ranger, Air Shepherd, since at night, turn on the light and fly towards the poacher to indicate to them that rangers are on the way. And they've shown us videos where the poacher will indeed run away. But if you always do this, try to deceive the poachers by turning on the light and flying towards them when there are no rangers. Poachers will figure out that this is really not a very credible threat. So we need to be strategic in our deceptive signaling. So this leads to this model, I'll call it signaling Stackelberg security game. And so the basic idea is generating a security game model with optimal deceptive signaling. And this is part of Haifeng Shu's PhD work, for example. And so here we have a set of poachers who are arriving in a park. It's an illustrative example. They have calculated the probability that ranger is present is 0.3, a ranger is not present is 0.7. They know the mixed strategy that was played. A drone flying overhead, though, not only knows the mixed strategy, also knows the pure strategy, whether the ranger is actually present or not. When the ranger is present, it's going to truthfully signal to the poachers, yes, there's a ranger present. When the ranger is not present, with this 0.7 probability here, 0.3 probability, it is still going to signal to the poachers that a ranger is present. These probabilities, so if you look at it from a poacher's perspective, half of the time they're being lied to as to whether the rangers are present or not, but still it is in the best interest of the poachers to believe the signal and run away, even though they know half of the time there is deception. The remaining time when there is no ranger, we are going to truthfully signal that there is no ranger. We can show when we are trying to compute an optimal defender strategy, multiple rangers, multiple drones to commit to in a national park, that this is an NP-hard problem even for zero-sum games. In recent work, we have extended the strategic signaling in presence of errors when there are errors in detecting adversaries. So this is a paper at EC'20, but remains an important area for future work. So with all of this progress being made in terms of predicting placement of snares, generating patrols, Spot for detecting poachers, there's excitement in our collaborators, in our conservation community collaborators to deploy this worldwide. As I mentioned, so we have been working with SMART, which is a collaboration of WWF, WCS, and other wildlife conservation agencies, and Microsoft's AI for Earth. We've integrated PAWS, the software that we've built for preventing wildlife poaching, to assist the rangers in their task of predicting where snares are kept and generating patrols with SMART. This platform, this software is now available for rangers to download worldwide. And so we hope this will start getting used in the 800 or so national parks that SMART is active in. In fact, these experiments have begun. We are getting very exciting results in terms of PAWS and predictions being used and generation of patrols. So it's a very exciting time, and I hope, again, an area where we may be able to collaborate with some of you. And hope this can be extended towards protecting forests and fisheries and so on. So I'll end here by challenges that I wanted to again bring up in terms of integrating learning of adversary models and game theoretic planning. This is learning adversary models with limited real-world data, network security games to prevent illegal smuggling. And I didn't get to active gathering of adversary information is another challenge. In terms of strategic signaling, there's uncertainty in real-time information to deal with, and cost-benefit trade-offs. Should we invest in signaling or should we invest in more protection? More rangers or more drones, for example? So I'll stop just the last couple of minutes. I hope the people were able to take away 3 key messages: that the research that this community is doing in multi-agent systems models, whether in terms of social networks or game theory, is very impactful for public health and for conservation projects. Field deployments, however, bring up very new, interesting challenges that I hope are of interest to this community. And finally, there's a wealth of new multi-agent research challenges. We have partnerships with NGOs. I'll end by making some observations about deploying AI research for social impact. First, it is possible to simultaneously advance AI research and achieve social impact. We have to therefore take a data to deployment perspective. The research is not just about improving algorithms, but goes all the way from data to understanding challenges in deployment and improving our models and algorithms. It's important to step out of the lab and into the field to actually understand the constraints that the NGOs and so forth are operating in. For example, a social network is just not available. To embrace interdisciplinary research, whether with social work or with conservation scientists, we find that lack of data is a norm and is a feature and must be a part of the project strategy. And when we deal with AI for social impact, this work should be evaluated differently and not just from the lens of algorithmic improvements. So I'll end by thanking all of the collaborators in the papers that I've cited, and really look forward to hearing your questions, reactions, and would love to collaborate with members of this community. Thank you for inviting me.